a whole question, but it's a topic or it's a part of a question that comes up. Suppose that you were doing a region D, and it was this region inside here. And it's built from, obviously, the x-axis. And that this line here is, say, y equals 3x, okay? And this line here is y equals, I don't know, 6 take away x, right? So that's this line here, y is 3x going that way, right? And this shaded region is the region D. And we need to set up limits of integration, right? That's a very common thing, right? Limits of integration for this region D. And you know, we talk about guys called type 1 and type 2. Type 1 would be vertical rectangles, and type 2 would be horizontal rectangles. And the reason I've chosen this one is to show you that sometimes vertical rectangles are not the way to go. Because what happens if you do a vertical rectangle here? Do you see after this point, doesn't the equation change? And that's not a good process. Whereas horizontal works really well. But if you're going to do horizontal, I guess I'll need to find that point. So let me figure out what that point is. Well, if you take 3x and you find out when does it intersect with that guy. Okay, there you go. This guy here is 3/2. So maybe you have to find it, that could happen. So I want to do horizontal rectangles. The y values are going to go from 0 to 3/2. And one of the two has to be a number, right? Because you're going to have to end with that integral, right? And the last integral must be numbers or you can't get an answer, right? It won't work. I'm going to go from here to here. But the equations I've got are not really in the format that they need to be, right? This line here is written down as y equals 6 minus x. But don't I need to call it x equals 6 take away y? You comfortable about the rearranging? And this guy says y equals 3x, which again is not really what I need. Don't I need x equals 1/3 y? And so the x's, this is the limit of x's, goes from this side to that side. And this side is the big one, right? So this goes on the big side. And this guy would be the little side. And that would be, maybe that is the answer, right? So you have a function and you're integrating, it's a double integral. Couldn't that be the x and the y and you've already done the z, right? The z goes from x plus y is, you know, x minus y, whatever it may be. That would be a situation like that. Let's suppose then, connected to that same idea, that you get 3x plus 6y or 2y plus 6z. Let's suppose it's equal to 12. Now we all recognize that as a plane. And let's say this plane is in the first octant. And I am interested, or we are interested in, what does that guy look like, right, on the XY plane, right? Because if we do that, so if you draw your 3D guy, and this works really well when it's a plane. If you want to know where it crosses the x-axis, don't you basically make those two guys 0? And you get the x is 4. And then you get y is 6. And then you get z is 2. So if you want to kind of imagine what this would look like, wouldn't it look like one of those funny little 4-sided dice things, right? Now, when it hits the floor, that's the region D. That's my kind of my theme today. If you go and you orientate things the way you need to, you're going to say, okay, it crosses the x at 4 and it crosses the y at 6. So the region that we're interested in, the guy we're going to call D, is actually that triangle there. Right? Now, what would this triangle look like? Well, could we do a horizontal or a vertical? Sure. Can we do both? Wouldn't matter. And since I'm lazy, whenever I can, I tend to go this way because it typically makes my life easy. So the x's limits of integration are 0 to 4. And the y's, well, go from this guy here, which is a straight line, to 0. And this guy here, we need to create its equation, right? And we've done this a few times. Don't you just need to know what the slope is and then add 6? Right, so this is a 6 by 4 going downhill. So this is -3/2. And then you add a 6. Now, let's suppose this question was, we're interested in finding the volume of this shape. So that's going to be a triple integral of 1, right? Now, if you wanted to find that, you would need to generate the limits of z as well, wouldn't you? Now, for this shape, it's a bit hard to draw, but can you imagine that's on the surface and you go vertically downwards? Isn't that line representing the limits of z, right? From the floor to the slope. And the floor is 0, and the slope you get from here. So you rearrange this guy. So if the question was the volume of that shape, you can do a triple integral of 1. And then you can do z goes from 0 to 2, take away a half x, take away third y. And then you can do whatever order you like, y or x. I'll do x because I want to. And then you would do y. And I just made a mistake there. Don't I actually have to do y first after that one? Right, because it's got x's in it. So let me do that guy with more room. Okay. I'm going to do x from 0 to 4 because it's the only one of the 3 that has numbers. I'm going to do y equals 0 to -3/2 x plus 6 because that has x's in it. And I'm going to do z equals 0 to z equals 2, take away a half x, take away 1/3 y, because that has x's and y's in it, right? So the guy that's got most, the guy that's got 1, the guy that's only got numbers, right? That is the only order that would make sense in this question, right? And if it's a volume, we just do 1 dz dy dx. Suppose it was a triple integral over a region, then doesn't that just get replaced by whatever f of x, y, z is? Right. If it's a 1, you're getting a volume. If it's a triple integral over a region, you just replace this by whatever function they tell you, right? Integrate this volume, right? Where the function is x plus 2y plus z, whatever it might be. And that's how you would get around it. But since this is a volume, I guess I'll return to 1. When do you use, we're talking triple integrals here. When do you use, here's the choices, that guy, okay, well, let's start at the bottom. When should you use a spherical coordinate system? What kind of 3D region would be suited to a spherical coordinate system? What would you need to integrate to want spherical coordinates? I wasn't expecting that question to be hard.
A
Must be,
sphere?
yeah.
Yeah.
A sphere, or part of a sphere, right? Sometimes a hemisphere. You see the word sphere in it, aren't you going to go spherical? Kind of, you know, it is what it is, right? When would you use cylindrical? A little bit harder to say, but when would you use it? And know if it's a cylinder, which is obvious, but other situations also go cylindrical.
When you have a circle.
Yeah. And typically, when you end up with a circle on the XY plane, right? So cones do that as well, don't they? Cones would make circles on the XY plane. Cylinders do. All sorts of shapes might do it. Paraboloid can sometimes make a circle when it hits the XY plane. So any shape that when you do the XY, like the shadow of it looking from above, if you saw a circle. And basically, aren't these kind of ones for the rest? Right. So you'd use dx, dy by dz if you were integrating like, you know, cubes and y equals x squared and polynomials and so on. I got this little list here. Here is the guys that you would use if it was spherical. I mean, they make a meal of this. I won't worry about this bit, but this is the important part, isn't it? When it's cylindrical, there's an r, dr, d, theta, and z is still z. Whereas when you go polar, everybody gets turned into rho, phi, or theta, right? Or some combination thereof, right? That'll be good. Right, so hopefully that's given you enough time to think of something else, because sometimes one question leads on to another idea. Has someone got something that they'd like me to go over now?
Can you do a Stokes theorem?
A Stokes theorem. This is 16.8. So in my little list of guys, quite near the end actually, so keep going. It can be that late. Oh, here we go. So we're looking at Stokes' theorem, and it says that, look, you can get a line integral by turning it into essentially this guy. But this isn't actually the guy that we use. Don't we turn this guy into another guy that is easier to work with? So that's essentially what we're going to be doing. Let's find an example of that type of question. Okay, so okay. We're going to start off with a question that looks like that, right? We're going to get that line integral. That line integral, according to Stokes' theorem, turns into a surface integral of the curl of f ds. That in turn then turns into a double integral over a region D, right, which is just a basic guy on the floor. You remember the start of today, the D's, that's what he's going to look like. And it's made up of a negative P, and I'm writing this down to make sure I don't screw it up, negative Q, and that's a G, see, D, Y, plus an R. And they say dA, but dA is basically dx dy. And the guy that they're calling G is actually the equation of the surface. And F is P, Q, and R, which is these guys. And D is the region typically on the XY plane. So we imagine the shape having, you're looking above it, you're looking at the shadow when it hits the floor. Right, so that's the theory behind it. So which one am I looking at? Does it really matter? Okay. No, I did that one last time. I don't want to do the same one twice. Okay, suppose we are going to find this fella. By the way, C has to be a closed loop, right? You can't have it hanging, right? That's, I guess, for obvious reasons. This fella, the vector field is 9y, xz, and x plus y. That's fine. And the curve C is the intersection of the plane y plus 9, and I believe it's x squared plus y squared equals 1. Now, if I drew that guy, which is really the only guy I need to worry about, can you see that the region D is going to be a circle? And it's going to be a unit circle. Oh, you might think about, what about the z, y plus 9? Can you imagine the z, y plus 9 just coming down at an angle and cutting it? But if you looked from above, would it still be a circle on the floor? So this really doesn't distort that answer, right? Can you imagine a cylinder being cut by some angled plane? The cut might look like an ellipse, but if you look at it from above, isn't it still a circle on the floor? Now, that does give me a little extra work to do. Since the region D is a unit circle, doesn't that lend itself to polar? And since it's a unit circle, I got that. So I will be doing the double integral using the formula that we have here. And this is going to have a whole load of x's and y's in it. Okay, this dx by dy, won't that just turn into r dr d theta? And won't this region D be described using these limits of integration, not limits of integration with x's and y's in it, right? So there's going to be a little bit of a and a little bit of b in that, but that's fine. So, before I go too far, there's this guy, there's this guy, and there's this guy. Right. Now, we need to know who this fella is. And this fella is hidden here. So this fella is the y plus 9 guy. Are we cool with that? And it's also called z equals y plus 9. Yeah, does it make it more obvious? Right, I think I've got all the pieces. We're going to calculate this double integral. Writing this guy down again, that way I can hide it. Instead of dx dy, I'm going to do r dr d theta. And these limits of integration are going to go r equals 0 to r equals 1, and theta equals 0 to theta equals 2 pi. I'm going to keep these guys here for a little while in terms of x's, y's, and z's, but then I'll turn them into r's and thetas later. So we're going to have a 0 to 2 pi. We're going to have a 0 to 1. Make sure I got the right guy. Yeah, I have this guy. So it's going to be negative 9y. Differentiate this guy with respect to x, which is 0. Oh, that's nice. Take away negative xz times differentiate this with respect to y, which gets you 1, plus r, which is, in this case, just x plus y, r dr d theta. That gets me nothing. That gets me negative xz plus an x plus a y, or dr d theta. My goal is now to turn all of this into r and theta. But I have one little awkwardness, which I need to take care of. Don't I have a z? And it's not uncommon to have z's. That z has to be turned into x's and y's, and then I can turn everybody into r's and thetas. So what is z equal to in terms of x and/or y? It's over here somewhere. What is z equal to?
Y plus 9.
Yeah. Z is essentially the gxy, right? Gxy is z, z is gxy, right? Z is the surface, you know, the plane that's causing the surface. So this is going to be y plus 9 plus an x plus a y, or dr d theta. Okay, so it's negative xy, that guy, plus that guy. Again, I'm putting far too many lines in, but it's better too much again than not enough. Okay, that's going to get me negative ax. So it's going to be negative r cos theta, that's x, times r sine theta, that's y, minus 8x's becomes negative 8 r cos theta, plus a y, which is going to get me an r sine theta, all times an r dr d theta. Would you agree the question's is ugly as heck, but isn't it now doable? Can't we just, you know, multiply these out and, you know, do what you need to do? And you get a big, long, horrible expression. Evidently, I don't believe it, but according to the one I'm looking at, ends up being pi. Go figure. Are we good? Right, the method is right, as I said. I should check now because I don't like looking at answers. Yep, yep. Y plus 1, yep. Okay, I can live with that. Okay, next question.
You go to green theorems, and number 10 kind of explained that a little better.
This one here.
Hold on. I showed it here.
So Green's theorem says if you want to do a line integral over a closed curve C, so
Oh no,
to do that. Not that one.
I meant the problem number 10 for scene 4.
Okay, let me go and find that guy. So we're talking Green's theorem 16.4.
And then number 10.
And number 10. Okay. Hope it's that guy. We'll find out.
Yes.
It's loading up. And the one I'm looking at is a find a centroid. Is that the question? My number 10
yes.
says, okay.
And a century.
Right. Okay. So what you have got here is they're telling you a formula for calculating the center of mass which is this guy, and that guy. So somebody went and used Green's theorem to create these two formulas, or maybe whatever theorem they used, and A is the area of D. So what we're going to have to look at here is what on earth is D? And D is described as a quarter circle, radius A in the first quadrant. Okay, so they're telling me that D is a quarter circle, radius A in the first quadrant. So that's what D looks like, okay? So I will do X bar, which is 1 over 2 times the area, that guy, X squared dy. So far, so good. And I will use my Green's theorem thing, this guy, in a minute. Oops, we seem to have lost it. A is the area of this guy. Well, isn't this a quarter of a circle? So it's a quarter pi r squared. And since the radius is A, it's 1/4 pi A squared. Are you comfortable about A just being that? Okay. So we are now going to be doing 1 over 2 times 1/4 pi A squared. A closed line integral of that guy. And that gets you a half and a half on the bottom. And can you trust me that you get this guy? The half becomes 2 on the top. We're good? Now, I'm now going to rewrite this guy in a slightly artificial form, but I need to. And you might say, why am I adding a 0 dx when 0 dx has no effect, right? Because it's nothing. The reason why I want to do that is that if I'm going to use this formula here, don't I need to know who the P is, and I need to know who the Q is. So my guy is now going to be 2 over pi A squared, a double integral over region D, which we haven't done the details of, this guy, and this guy is P, that's this one, and this guy is Q. So it's dq, that's this guy, with respect to x gets me 2x. And doesn't this guy with respect to y or any other thing get me nothing? So I basically just have 2x, right? 2x take away 0. And now I guess I could call it dx dy for a little while. But wouldn't a quarter circle work much better in polar? So the region D is going to be r equals 0 to a, and theta is going to go from 0 to pi upon 2. Are you comfortable with that? So we now have 2 pi a squared, the integral from theta from 0 to pi upon 2, r going from 0 to a, 2x, and turn it into polar, r dr d theta. See, I'm only doing one little piece at a time. Normally you could chuck 2 or 3 of these lines into one. Are we good? Now, all I need to do now is turn that into 2r cos theta times an r dr d theta. Do you want me to keep going, or getting to that stage, is that good enough? Your choice, Christian. Do you want me to keep going, or is that good enough?
I think I understand it now.
Okay. According to what I've got here, this guy times whatever this is, because they're only telling me the answer here, is 4, I've lost it, 4a over 3 pi. So I should be able to figure out what's missing. You're going to have a 2 here, you're going to have a third here, and you're going to have an a cubed. So evidently all of this ends up just being 2/3 a cubed. And 1 to the pi. That's all as a pi. So evidently there's no pi involved. Why not? Oh, because there's a cosine and it's 0 to pi upon 2. That's perfect because you get 1 out of that. So this is probably where all the fun starts. In fact, I can see it. Can you not see cubed and 3 in the bottom? 2/3 r cubed. That gets you this guy. Take away nothing. That just gets you 1. Perfect. Makes sense. It works.
Yep.
And if you did the y bar, wouldn't you just rearrange it a little bit? If a guy's missing, can't you just call him 0? So that you can do the entire formula. Doesn't it need a P and a Q to do the transfer? So even if it's missing, which it was, give it 0. 0 dx or 0 dy, whichever one makes more sense in the context. Okay. That one actually turned out a lot nicer. I should stop looking at answers. That's the moral of this story.
Thank you.
Right, where are we off to now?
Can we do?
I have one.
We've got Maggie and David. Maggie kind of beat you to the punch there. So we'll give her a shot first and I'll do yours straight after it, David, okay?
Okay.
Right, what you got, Maggie?
All right, can we do the second question from last week's test?
That's very specific, but yes. Last week's test was test 9. Okay, I've got that loaded up. And what question was it again?
Number 2.
So it's find one of these guys. One of those flux things. F is, I have X, Z, X, and Y. And I have a hemisphere, right? Half a circle, XY plane. It's not, it's orientated differently. That's what the problem was, okay. So we have a hemisphere, half a sphere. And they're doing a Y greater than or equal to 0. So I'm going to try my best to orientate what kind of half circle we are looking at here. We are looking at a half circle, which is on the back wall coming out like this. Imagine it against the XZ plane coming outwards, right? Now, what is happening here is that they are doing, and we are going to do it as spherical coordinate system, but we kind of have to change who's the X, who's the Y, who's the Z, because normally you would do it from the floor going up, right? And that's where the trick is. So I'm getting my little list of guys so I don't screw up on who's who. And spherical coordinates are here. And the original looks like this. X is this fella. Y is this fella. And Z is this fella. Now, in my new orientation, isn't the Y doing the same job as the Z? So all I'm going to do is keep him alone, right? Leave this guy untouched. And I'm going to say, you're doing what Z used to do, and you're doing what Y used to do. Now, by doing that, I can pretty much keep the limits of integration the same numbers I would have done if it had been vertical. All I have to do is to remember that y gets turned into this and z gets turned into that, right? So let's look at this hemisphere then and what that would look like. Well, rho is all about the radius. And if I've got this guy right, this is 25. The radius here is 5. So we're happy about rho being from 0 to 5. Now, it's a whole circle. So theta is going to be, as it always is for a hemisphere, everybody. So who is phi going to be? Well, normally you do it vertically, right? You start out at 0, and don't you only get to pi upon 2 if you want half a sphere? So do you see, I don't need to change these numbers. I only need to change who I'm using in each location. In this case, it's the y and the z that are changing places. Because y is like the z, right? It's like the up thing. Are we good with that? And we have a dv guy going on, and the dv guy is totally fine. And the dv guy is still the same dv guy, and why haven't I got it in my list? Okay, it is rho sine squared phi d rho d theta d phi. Did I get it right? I never remember these things. Someone look it up somewhere else. I don't have it in front of me. I guess I should look at their answers. Of course, they skipped all those lines, they do. Please tell me that's the right one. Otherwise, I'm going to have to spend a few minutes finding one.
I remember from doing this question that is that, yes.
Oh, thank goodness for that. Well, I got lucky. Right.
You can double check on my note card.
Right. What you would be doing in the final, wouldn't you have a note card with that guy on it, right? So you would just go find it. Right.
Isn't it rho squared sine phi, not
Oh,
rho sine squared phi?
Oh,
yes.
okay. Pretty close, but
Okay.
somewhere, right?
I was really confused. I was like, is that right? Are all of
No.
my notes wrong?
No, if that's in your notes. I honestly, I never remember these things. I should. I could derive them if I wanted to. Couldn't I just do a 3x3 Jacobian and, you know, eventually I'd get the answer? But that's a lot of work every time you want to find something. So hopefully we've got all the pieces, and we're going to put them together. Get that out of the way. And I've almost forgotten where we are. We are in question. We're in question 2, aren't we? Yeah. So this guy, and we are in, I've lost my place here. Where's my, there we are. Oh, I won again. Still going to get it. I don't want to write the wrong thing down, as you've already seen me do. So, you know, it's going to be the last one I find. It's kind of guaranteed. Okay, here we are. Isn't it this guy? Going to turn into this guy. So the limits of integration are going to be rho equals 0 to rho equals 5. Theta equals 0 to 2 pi. Phi equals 0 to pi upon 2. That's good. I'm going to be putting in the divergence of f here. And then instead of my dv, there's going to be a rho squared sine of phi, very small writing, dr d theta d phi. So I guess I should find what the divergence is. And if you take this guy, it's going to be dp by dx by dq by dy by dr by dz. And if you differentiate, that's p, that's q, that's r. That guy gets you z. This guy gets you nothing. And this guy gets you nothing. So it looks like the divergence is just z. And z is going to be rho sine phi sine theta, right? So my integral is going to go from phi equals 0 to pi upon 2, from theta equals 0 to 2 pi, from rho equals 0 to rho equals 5. The divergence, which is this guy, times this. Okay, I think the back is broken. Would you agree you could just combine the rows, combine the phi's and have the sine theta, and couldn't you do a variable separable on it? And according to what I have in front of me at least, oh no. The answer ends up being 0. So it must have been a convergent field, or a conservative field, I should say. Okay. David, we got time for you, and that's going to be it. So hopefully I'll do it as quick as I can. Sorry for
Number
taking so long
7
with
on
that.
that same test.
Okay, number 7. So we're doing another one of these guys. Right. What do we have? We have a vector field F, which is really quite messy. It's that guy, it's that guy, and it's that guy. And S is another hemisphere. And so it's a hemisphere generated by this guy, and it's orientated in the positive x-axis, which is almost an exact carbon copy of this one, except your sphere is now going to be pointing that way. So what that tells me is, instead of using this, swap the x and z's around, right? So make the z this guy and make the x that guy. And these numbers can stay put, they're a hemisphere. Let's do the divergence of this guy. That'll be P, that'll be Q, and that'll be R. You differentiate this with X, you differentiate this with Y, and you differentiate this with R, with Z. Do this one with X, and you get Y, e to the XY cos Z. Oh, God in Hamill. And you do this one, you get 0, and this one you get 0. Okay, so it's still ugly, but at least there's only one piece to it. So I'm going to get an integral from, this particular one has a radius of 3. So it's going to be phi equals 0 to pi upon 2. Theta equals 0 to 2 pi. Rho is going to be 0 to 3. That guy there. Multiplied by that same rho squared sine phi and the stuff I don't have room for. This here needs to be turned into rhos, thetas, and phi's, and God in Himmel, that is ugly. Until I looked at the answer, in which case the answer is 0. And if I'd made my life easy, wouldn't I have checked that it was a conservative field before I started doing anything? In which case I would have found out the answer was 0. And I shouldn't have needed to do anything like that. I assume the 0 comes out of something like, if you do the integral from 0 to 2 pi of a function like sine theta or cosine theta, won't that integral always end up getting you 0? In which case you don't care what the other two things are, because 0 times other things is still 0. So I wonder if that's the shortcut, if you don't want to check it's conservative, is look at your integral and see if you can get a guy that looks like that. Right, if you pull out the theta, I don't think it's going to be a phi because I'm looking at the limits of phi, but I'm looking at these. Isn't that a good candidate for having just a sine theta or a cosine theta in here? I suspect that's where the 0 came from, and it might be okay. And it might actually be caused by that guy. I can imagine plugging a number in here and a number in here, and that ends up being 0. It might happen that way too. I wish I'd given you more time, but maybe at least enough to get started on in that last one, David. We can go back to it on Monday, which brings me to, we have one last test to do, and that is your online test 10, which is up there, invisible. And Monday is an open day, so turn up with good questions. If you don't, you'll still get attendance. Turn up and ask the only question you want to know. If that's what it is, David, get it done, and then you can leave and go back to studying.